So now let's introduce lighting. We have perspective projection in place. We have the model in the center of the world, and so let's go ahead and do that and look at the lighting model. And we're going to implement the simplest lighting model that we have called Lambertian lighting, based on the Lambert reflection or reflectance model. So we're going to talk about that in a minute. Let me see and show you, however, what happens when we switch on triangles now, so that you get a good idea on the wireframe. Looks nice, but of course, when we render this now as triangles, all we get is a bright red, continuous red blob, where basically all the triangles that we saw on the screen are just filled in. And and of course, that's not true for real-life objects. In real-life objects, the brightness of parts of a surface is directly proportional to the direction of the light that actually shines on the surface. So, and there's basically a cosine law saying that, well, if it's grazing in parallel to the surface, none of that light's going to hit you, so the surface is going to look dark. And as the angle gets steeper and steeper with respect to your eye, then the surface gets brighter and brighter, and that's exactly what we're going to implement, because that's basically Lambert's observation in terms of reflectance, and we're going to just put that into our shader. And so let's do that and go back and go to the next step, where we add the Lambertian lighting model. So this is now the time where things are getting ever more complex, right? So as far as the code goes, I said that now the whole thing is dependent on the light position and the surface orientation relative to that light, and we're going to do that right here. So we have yet another uniform, and so that specifies our light position right there. And right now we're putting our light in the world coordinates at x equals 0, y equals 0, and z equals 3, which, given the default OpenGL lighting, remember that our eyes right now is at 0, 0, 1, looking down the negative z-axis. And so the light is right behind us. And then we now will have to use the normal matrix, so we're going to see how that works out. So the light position is one thing. The other thing that we have to take into account is the surface normals now. So the surface normals now come into play. But before we can use when we use the surface normals, we have to make sure that our surface normals are actually expressed in world coordinates and with respect to our view. And that leads to a problem ultimately, because of our projection matrix. So we must make sure that we have the normals available to us in world space, however, which are not subject to projection. So we need to basically save that. And it's a little bit more complicated than that because of the nature of the perspective projection. I'm not going to go too much into details, but the point is that we have to create a special transform for our normals that will do the right thing under these circumstances, and it's built into Qt. The book really doesn't talk all that much about it, and I'll post a link to a good explanation for this. But it's good enough to say that, okay, we need a separate matrix to separate out the matrix projection, the normal projection from the view projection. So from the perspective projection. And so that happens ultimately here, and we have yet another uniform for this normal matrix. So that's right there. So as far as drawing goes, then let's look at the shader first. So here's our normal matrix right there, and our light position. And then what we get here is, so we are basically taking the vertex that comes in, that's stored in our vertex array, and apply the model view projection, which puts that vertex into world space or view space. And we do the same thing then for the normal. So we're basically taking our normal vector, multiply it by the normal matrix, and normalize it again. And that puts everything into the corresponding world space normals. The comment in the code basically says that if your model and view matrix does not contain scaling, then you can just take the 3x3 submatrix of the model view matrix and use that for normals. But since we want to prepare for the general case here, we're just going to use the actual normal matrix, which we'll compute and set in the program, as you'll see. So then comes our lighting model. So we basically in the Lambertian lighting model have two components. The first one is ambient lights. That's light that's all around you, that's not directed. And we set this value here to 0.2 right now, meaning that even if we don't have any directional light, we still see like sort of kind of like an outline of the object because of the ambient light. And then the actual reflectance is called albedo. And so we're setting a diffuse albedo of 0.8 here, which is the intensity of the reflected light of the surface. So it's a measure of surface reflectivity. We calculate the light vector, which is the vector from the vertex to the light. We take the dot product of the light vector and the surface normal vector that we've computed when we established the model. We set the model color to red, and then here comes the computation. So the model color times the ambient plus the model color times the dot product, which is actually the cosine of the angle between the light and the surface normal, times the diffuse albedo. And that's that. We clamp that between 0 and 1 just to make sure that the value is in the expected range. And then pass that to the vertex shader to colorize it, which happens here. So we have an output variable defined for the color, and then we pass the vertex shader to the vertex to the next phase by multiplying the vertex in view space already, and now do the projection down the road further on. So and the vertex shader, the fragment shader then, this time around is a little bit less trivial than previously. So the fragment shader now takes the vertex shader color output and just passes that on to the rasterizer. So, and let's look at the code where we compute the normal matrix. So here is our model view matrix that we rotate and translate. And this time around, I also set up a lookup transform so that we now have a way to look at our scene from a different location than the default. So we're setting our LookAt actually at 0 0 and 2, so 2 meters along the z-axis. We're looking towards the center of the scene, which is what this one here is. So this is the center of the scene, 0, 0, 0, of course, and up is the, as always in OpenGL, unless we specify otherwise, up is considered the positive y-axis. We rotate our model. After we translate our model, we rotate it twice, once around x and once around y, so that we get a nice view of the default view of the teapot, so that we can see a little bit more complexity. Then we set our model view matrix, the projection matrix, and then we compute the normal matrix out of the model view matrix, because remember, the model view matrix transforms everything into world coordinates. We need the normals in terms of world coordinates, and that's happening right there. And set that and transfer it into the shader program. And again, also set our light position as we've had before. So the light is still behind us. So we enable backface culling right here. So if the surface is not oriented towards us, it will not be drawn. So and that actually is independent of the that is actually independent of the actual surface normal, because it depends on the winding. Once I've read in the model and started rendering it, I started realizing that the patches in the model are wound clockwise. The default in OpenGL is counterclockwise. So you set the winding for backface culling to clockwise, which happens here. So the default is counterclockwise, CCW. And then we enable backface culling. And then we draw our elements this time around again as triangles. And so the Lambertian lighting model then actually works quite impressively. So when we actually compile and run this, we'll actually see that we now get a fairly decently rendered model that looks very, very smooth. And it's really hard for us from the color to see that this is a fairly rough approximation of the thing. And this is where the surface normal averaging comes in, because remember that we store the surface normals on a per vertex basis as the average of the adjacent patches. So there are no sharp changes of surface normals at the vertices themselves, and the fragment shader then takes care of the linear interpolation of when it assigns the color of the linear interpolation between the colors at the different vertices based on the normals. So that gives this very, very smooth appearance, although the model is really not very smooth at all. So very impressive and very nice, because the graphics hardware does all of this for us automatically. So and that's the basics behind the Lambert model. At this point, you are well equipped to carry that on into modifying it for Blin Phong. But before we do that, let's do one more thing, and that is actually show you how to get the sliders to work, so that we can play around with the model and actually move around, rotate the model and move around the light source.